Hello everyone. In this video, we will introduce probability measure and we will study properties of probability measure. Well, let us start with a sample space. Always in the probability theory, we fix a sample space. Let S be a sample space. Well, recall the universal set in the set theory. Sample space is playing the role of universal set in the probability theory. Then a probability measure is a function that to each event E, remember event means subsets of S, assigns a number PR E, we call it probability of A, with the properties the following properties. So what it does is that to every event, every subset, it tells you what is probability that, what is a number that we call probability of E. But these numbers must satisfy the following properties. First of all, probability of any event must be a number bigger than equal 0 or less than equal to 1 and less than equal to 1. Yes. And well, in particular, we are interested in the cases that probability of sample space, the whole event, the largest event possible, must be equal to 1. Then the second property is probability of complement of an event is 1 minus probability of event itself. Okay, and the third thing is probability of a union of two events is given by this formula, probability of E, probability of F, you add these two minus probability of E intersect F. Well, these last two properties you should recall from the number of elements for a set. So remember that there we had n of E complement was equal to nu minus ne, and we had n of A union B, or let me just use E and F again, was probability of, or number of entries or elements of E, number of elements of F minus intersection. So these two properties are very related, but since you have already seen these ones, you can keep those ones as kind of the same formulas, with one difference. The probability is always a number between 0 and 1, but the number of elements of a set can be any positive integer number. Yes? Okay. Well, there are a few things that I should add before we end this video. So remark one is that well, in the property 1, the probability of S is 1, and if I combine it with property 2, I can find what is probability of empty set, the empty set. If E is equal to S, then probability of S complement using property 2 must be equal to 1 minus probability of S. Probability of S complement, well, S is universal set here. The complement of that will be empty set, 1 minus. So if I use the property 1 actually here, if I use property 1, I know the probability of the whole sample space is 1. So 1 minus 1, 0. So this tells me that probability of empty set is 0. So that's another property that we can get from the properties of probability measure. Another result is now I can combine remark 1 with property 3. So if two events E and F are mutually exclusive, it means that, well, it has a meaning here. It means that E and F, their intersection is empty set. Then, you see, if I apply the formula 3, probability of E intersect F must be equal to probability of E plus probability of F minus probability of intersection, yes. But for mutually exclusive ones, we know that this is empty set, and that probability of empty set by remark 1 is 0. So as a result of this, probability of union for the mutually exclusive events E and F are mutually exclusive. For those ones, you don't need to be worried about the intersection. The probability of intersection is 0. So that is another thing that having it in mind will help you to do some more work. And the last remark that I have here for you is, well, if you have two events, for any two events, E and F, well, you can easily see that E intersect F and E intersect F complement are mutually exclusive. This you can do in different ways. You can use Venn diagram or just properties of intersection. You will see that if you find the intersection of these two, it will have a part that F and F complement must intersect, but there's no intersection there. And we know from the set theory that the union of these two guys is equal to E itself. So if I combine this with remark 2, I'll see that probability of E, which is union of those two, must be equal to probability of E intersect F plus probability of E intersect F complement. Then they're mutually exclusive, so I don't need to bring in any other intersection term. So that will be just what we have. And remember that we had a similar formula for the number of sets. So recall that we had NE, elements of E are either in E and F or in E but not in F. So that is also another similar formula that we had for number of elements of a set. Okay, so these were the properties. In other videos we will do some examples and use these properties.